We'll go over the answers. Hopefully that sheet that I put up there with all the reactions written out in one place was helpful. So here we are removing the NH2, that's the key. So it's a reduction of some sort, and it goes through the diazotization. So we use sodium nitrite and HCl. Which is basically just a way of making nitrous acid. Nitrous acid isn't stable, so you can't go buy a bottle of nitrous acid. You got to make nitrous acid from sodium nitrate. And then we'll work that up with H3PO2, which is hypophosphorus acid. And obviously that doesn't have as many oxygens on the phosphorus as you typically expect, right? Phosphoric is PO4 and phosphorus is PO3, so that's a reducing acid. Here we're doing a reduction from an NO2 to an NH2. There's a bunch of different ways you could do that. Clemmensen reduction will work. Zinc amalgam and HCl, that's the Clemmensen reduction, but you could also use solid iron and HCl. Basically, you just need a metal that's easily oxidized. The other product is zinc oxide, just like it would be for the hydroboration reaction where we use zinc solid as a workup step. So in order to reduce this, we got to oxidize the metal. Or you could use rainy nickel. It doesn't have to be rainy nickel either. It could be platinum oxide or palladium on carbon, one of those other. 10% palladium on carbon also works really well in the presence of H2 gas, and it doesn't even require very much pressure because the NO2 group is pretty easily reduced to the NH2 group. So there's lots of different ways to do that. This is a calculation. We're going to react the alcohol with BF3, and that will turn that OH group into a leaving group so it can fall off to generate the isopropyl cation, and then the isopropyl cation is attacked by the ring. So there is actually a cation intermediate in this one, unlike the Friedel-Crafts reaction where the cation is never actually formed. Yeah?
So on the quiz, the double bonds were like different, where the ring was like flipped a little bit, so like, yeah,
there's always a resonance structure where you can switch those double bonds because it's aromatic. And sometimes if you're not using the hydrogen, right, if you're not actually showing any mechanism on this, we can also shortcut it. You'll see it written with just a circle in there, showing that it's the hybrid between these two resonance structures, and you've got that ring. So these three are all equivalent ways of representing. This molecule is actually called cumene. It comes from cumin, not surprisingly. This is actually a Friedel-Crafts reaction. So we form the acylium ion in there. And then that acylium ion is attacked. And this one does require stoichiometric quantities of the aluminum chloride because the oxygen there complexes to the aluminum chloride and makes it unavailable to do the remaining reaction. Here we're sulfonating fuming sulfuric acid with a mixture of SO3 gas and H2SO4 liquid. Right? So we've consumed all the water by reacting with SO3 gas, and then the electrophile is SO3. NH2 converting to a bromide, that's a Sandmeyer reaction. So it's the same first step as this reduction where we're taking the NH2 group and replacing it with hydrogen, but the second step is now copper 1 bromide or cuprous bromide. And you can do that with cuprous chloride or cuprous cyanide as well to introduce chloride or cyanide groups there. If you're doing it and you want an iodine, you don't actually need the copper salt for the iodine. You just use NaNO2 and HI instead. So you've got the iodide present, and then that I plus is, or that I minus is there to attack. Here we're chlorinating, so we need Cl2 gas, and then any of the possible Lewis acids. You can use tin chloride, stannic chloride, you can use Stibus chloride, SbCl5, or AlCl3, or FeCl3. whole bunch of different possible choices. One of those, you don't need all four, right, will allow you to activate this by attaching that Cl2 to the metal. So it's a non-metal or a metal, in this case metals, in this case metalloids or non-metals, right, to create a complex ion. This is a reduction, and again, there are multiple ways of doing that reduction. Zinc amalgam in HCl is the actual Clemenson reduction, so that's one way to do it, but you could also use iron in HCl, usually aqueous. Or alternatively, you could use the Wolff-Kishner reduction. Or if you want, you can use the dithiane. You can make the dithiane in the first step. And then do the desulfurization with radionickel nickel and H2 to take that dithiane group off. So probably these two are more commonly used than those because these are cheap and the other things are less cheap. But any of those methods of reducing that will work. Here we're oxidizing it, right? That's the opposite. Formic anhydride plus H2SO4. Aqueous. Yeah. Sorry, I can't hear you from all the way up here. Okay. Yes, but that'll work too. So Shiwei pointed out that in the textbook, you can also reduce this directly without going through the dithiate with the Adams catalyst, platinum oxide, and hydrogen gas. Normally, that will not reduce a carbonyl group all the way to a CH2. Normally, that will just reduce it to the alcohol. But because it's in the benzylic position next to the aromatic ring, this will reduce it all the way. Here we're doing an oxidation. The peroxy acid is what you need for that, CF3CO3H. It doesn't have to be this peroxy acid, but that is one of the more common peroxy acids. The trifluoro group makes it that much more acidic and makes this oxygen that more positively charged. So those are the reactions. This one I actually gave you the reaction and asked you for the mechanism. So the first step in the battle is to correctly draw the structure of nitric acid without expanding the octet on nitrogen, since you can't expand the octet on the nitrogen. We're then going to protonate that using the sulfuric acid. That's not a very favorable equilibrium. Because nitric acid was already a pretty strong acid before we protonated it. We're now going to break this down by pulling that hydrogen off. And you'll notice that's actually 6 electrons kind of flowing around in that ring, which makes it an aromatic transition state. So that's one of the reasons it happens. Right, now that we only have 2 things attached to the nitrogen, we can put double bonds on both sides to make the nitronium ion. And then the benzene ring will attack that. Because of that inability to expand the octet, though, it's important that when you attack the nitrogen, you also break one of the pi bonds to the oxygen, so you don't end up with 5 bonds to nitrogen. So that breaks the aromaticity. You have an sp3 hybridized atom in there, so it's now non-aromatic, which raises the energy substantially. We need to take that hydrogen off in order to regenerate the aromatic ring. So it's 4 steps, 2 steps to generate the nitronium ion, and then the standard 2 steps, right? The electrophile gets attacked by the ring, and then the hydrogen is removed to regenerate aromaticity. Yeah.
I know we use the water to put the hydrogen back on the ring, but couldn't you also use the sulfuric acid if you want? Or does it really matter?
It doesn't matter. So there's also that in solution, and if that collides with it before water does, you end up with sulfuric acid. The reason I used water is because there's probably more water around than there is of this, since there's already 29% water and another 2% from the sulfuric acid, whereas we're probably not generating a huge amount of that by deprotonating. So, but no, it doesn't matter. Either of those two bases are present, and they will work. I mean, if you really wanted to, you could actually just use nitric acid, right? Have this take that hydrogen off, and then you regenerate your nitronium ion. It all depends on what collides with it first, really. So that's the quiz. Hopefully not too bad.